I would like to speak following the lecture by Ms. Professor Christian Russo on the power of mathematics. And please allow me to speak of the joy and motivation. When I study mathematics, what is the joy and motivation I have in the pursuit of mathematical science? Well, when viewed from the world outside of mathematics, what do we find? Things concerned with mathematics. Well, we didn't have computers in the past, and everything was done in an analog manner. But today we are in the world of digitization. Let me give an analog of vehicles. In the 1970s and 1980s, engines were controlled by microcomputers. And that was made possible because of the advancements of hardware. And then there was another development. That is the change from the combustion engine to hybrid vehicles, and then electric cars, and then we are moving toward driverless vehicles. And we now have to control computers which control hardware. Hardware and CPUs were controlled by the most optimum machine language, but with the development of hardware, more general programming language can be used instead of a very specific machine language. So those are the changes we see. Then, do computers do all calculations, and can we do away with mathematics? Well, the answers may depend upon the audience we are talking to when I give this question, but for the general public, if you say whether the mathematics are necessary, and then I have to say that mathematics are necessary because we have to deal with unexpected events. But from the position of engineers and scientists, the answers are somewhat different. So I'd like to answer in the following manner. Professor Russo has shown us the wonderful results of simulations. And of course, simulations are run by computers, but the fundamental algorithms are necessary for the computer to execute. Simulations and algorithms are developed by mathematicians or mathematical scientists. Furthermore, there is a question for which we do not know whether there is any solution. And also, a solution can be found only after a very complicated conditions are set. So we do not know if there is a question at all. And even if there is a solution, and if I draw an example from Professor Russo's examples, if you change subtle conditions, there could be unexpected result. For instance, the estimates of errors. Complete information and complete and perfect algorithm do not exist. So we need simulations based upon mathematical sciences. However, simulations are not enough. In fact, mathematical models have to be developed or validated or have to be evaluated by the use of mathematics. So those are the situations where we feel that mathematics are necessary. So that's the view of mathematics viewed from outside the mathematical community. What about the mathematicians? When we mathematicians try to speak of the wonderful characteristics of mathematics to general public, we take two features of mathematics. One is the usefulness appeal. utility appeal. Mathematics, for instance, has a role to describe nature, and also mathematics can find diverse applications. The other aspect is artistics, part of mathematics. The beauty can be found in a logical structure, or we can find beauty in mathematical ideas. The mathematicians may have different views, and some people may say that those are just the views of mathematical geeks. However, usefulness, does mathematics come handy in a short span of time? But it may be no, but in the 50 or 100 years of time, mathematics could become very useful. Then why do we pursue mathematical questions and mathematical research? There could be various answers. It's not that those are my answers. For instance, for prestige. Of course, we are not doing math only for the purpose of prestige, and another motivation could be money. But I don't think people want to become a mathematician just to earn money, but that's one possible answer. And the third is for the feeling of accomplishment. When you did something wonderful as a child, you may remember that as a success experience and want to become a mathematician and want to be useful. And actually, there are mathematical results or research which could be useful. And the fifth reason is out of intellectual academic curiosity. This is in bold letters because this applies to me. And there are many mathematicians who do math because of intellectual curiosity. But curiosity, for instance, what the world would be like, that could be a very general curiosity, but there could be special curiosities about special problems. So those are some motivations which drive us for the study of mathematics. But then, as many people ask us, is mathematical research worth receiving any support? If mathematicians are doing this research only for their curiosity, it may not worth supporting. For instance, governments, tax money, support and grant. We have to be accountable for receiving and spending such a money. And science and technology policy, the fifth National Science and Technology Policy was launched in April this year by the government. And in that policy, mathematical sciences are viewed as one of the very important academic discipline, which is the foundation of many other academic disciplines and studies. But of course, some people may get offended when they hear that we are doing mathematics only for our curiosity. And also, even if it's useful, some may not want to support mathematics. And also, support by private foundations such as Inamori Foundation. Of course, support from such a foundation has to be given approval and cannot be decided only by the president of the foundation. And of course, accountability has to be met. So they have to scrutinize whether a certain mathematical research was supporting.
And there is no clear answers to this straight question, but these are my answers. There are four answers. So first of all, mathematics. It's usually applied in unexpected areas and in different ways, diverse ways. And as the Professor Yamada said, the current society is supported by mathematics as a background. as a background science. And this is a little bit different from other sciences. Mathematics is very abstract. So although it is useful, but it is basically invisible, and it doesn't have a direct impact on societies. It's usually contribute to society indirectly. And the word breakthrough, this becomes now a T word. Everybody say breakthrough, but the real breakthrough is very difficult. But when a breakthrough takes place, so we usually come to a breakthrough in an unexpected ways, meaning that a new idea will be required in order to make a breakthrough. So new idea comes from the pure mathematics in often time. For example, Fourier transformation or Fourier transform, this is the name of a technology. The technology was developed in 1800s, and this is now used to study the waves. And this is applied in oscilloscope. But nowadays, it is applied in MRI because Fourier transform basically detect different frequencies. For example, when you listen to orchestra music, there's different frequencies, but Fourier transform can detect different frequencies. And by using this technology, MRI algorithm is developed. And this algorithm, once it is there, you are able to take the images real time in MRI. The another one is algebraic geometry. This is my specialty. And this has been thought to be not related to the society or real world, but actually algebraic geometry is applied to the coding theory and cryptography. So it is used in computer for efficiency of a computer, or the optimal way to set the password in a computer, for example. Encoding theory and cryptography. And if you have objectives, if you start from these objectives, and do you think we can come to algebraic geometry? I don't think so. Algebraic geometry is there, and that is happen to be applied in these theories. And it is very difficult to distinguish a pure math from the applied math. So it exists as a whole, as a mathematic. So math is a one entity. So it has developed as one independent entity. There's no distinction between pure and applied mathematics. And in a different way, math is a tree. It's like a tree. So once tree grows and it's yield fruits. So those fruits are applications. So in thinking that way, you can understand what math is. And of course, another basic research is also the tree, but math is peculiar. And let me introduce Dr. Kiyoshito. He is very famous due to Ito's lemma or Ito calculus. But he wanted to understand essence of probability, and during the wartime in 1942, he published Ito lemma. And then he published in a shabby science magazine. And then in 1973, Black and Scholes applied his theory in financial engineering. In what way? They applied in estimating the prices of derivatives. So in order to predict what's going to happen in 6 months' time or 1 year times, derivatives, for derivatives, they need to forecast prices like 6 months out or 12 months out, and then they applied his theory and come up with a theory in financial engineering, and they won the Nobel Prize in Economics 1997. And Dr. Ito got the first Gauss Prize by IMU in 2006. And Gauss Prize is given to research which had a positive impact on different areas. And Dr. Ito was the first winner of this prize. So his research was highly valued around the time. And actually, Dr. Ito is the most famous mathematician in the Wall Street of the US. So based on those introductory talk, let me go to the next topic. So in my case, my research has been driven by curiosity. So let me go a little bit deeper. And first of all, my research area is the algebraic variety and algebraic geometry. I study algebraic variety. But what is it? Simply speaking, it's an algebraic figure. But what is it? Algebraic figure is given by the polynomial equation. So this is a collection of solutions. And it is not easy to draw, but just taking one example. This is a simple example. So this is the x squared plus y squared, but this is too simple. Therefore, it's a little bit more advanced. So y squared equal to the x plus 8 in bracket multiplied by x minus 1 in bracket. The high school student might difficult to draw a figure based on that because this is y squared. So this is symmetric to the y-axis. And so minus 8 to minus 0. So this is the way you can draw. And these are real number solutions if you draw these lines. But we're working on the complex number solutions. So it's not easy to draw, but you can still draw this kind of figures. And in algebraic geometry, we use both real number solutions and complex number solutions. Or if you go wild, we have the characteristic solution as well. So the algebraic variety. So my basic position is, well, my study is to detect how variety is curved. I won't go into detail, but an X, excuse me, I forgot to tell something in the previous slide. This is important. So this is an equation. So one equation, there are two variables in one equation. So whether you call it a curve or a surface, there are different opinions. But x is only free variable, and y is determined by x. So there's only one and a free variable. So this is a single dimension. So this is straight lines in the algebraic geometry. So going back here, you have P if you decide P and how it is curved. So positively curved means that, so usually these are headed up, meaning that it is pointed towards down. So this is what is called a positively curved. And next one is a saddle type. So in one side it is pointing up, and then another side it is pointing down. So this is what is called negatively curved. And neither of these are called a zero. So simply speaking, there are three types of curves. And this is the general pattern. And if you have this positively curved, so here is like a bubble. And minimum model is my research area. So what is it? So roughly speaking, so it is curving in different directions. And why? So minimum model is in this figure. It may make confusion, but if you have a membrane here, film here, or if you have a film on a flame and it's a shape like this, and if you push from the bottom, then area will be shrunk, meaning that this shape won't be like this. In order to make it smaller in areas, you don't have this kind of figure. Therefore, the figure must be in this type, saddle type, negatively curved one. So that is my interest. So why my interest? Or how did my interest grow? In the beginning, I studied Franco conjecture. I tackled with Franco conjecture in the beginning. So it says if a variety is positively curved in a very strong sense, meaning that so in different areas or in all areas, if the curve is in that shape, then it should be unique in each dimension, like an n dimension or projective space, what we call it. So there's only one. So that is the Franco conjecture. And I myself and Yao and Chu solve this problem. And this is a very specific problem. So positively curved figures. So in dimension, there's only a unique. And then I move to more general question or general problem, and I studied a variety which is positively curved in a weak sense. So my interest grew in that direction, and finally the minimum model program was developed, and this is applied to study algebraic varieties nowadays. This is a fundamental tool, so I started with very specific problems, but I came out with some kind of very generic.
Then what specific problems I have looked at? That is the invariance. Invariant is a general term, but in other words, I try to consider the cone of curves. It's a cone, so it has such a shape, but it's not at random. From one vertex, there are many lines coming out. The important point is right here. There is such a space defined by lines, and there are two spaces divided. And on the right, this space is somewhat curved. In the left, some polyhedral kind of form. And please ignore C1. And in the left, this corner line is called the ridge line. And the ridge line is called the extremal ray. And so suppose that there is an algebraic variety, and we can draw such a cone of curves, and there are such rigid lines, and if there is such a rigid line, it has a geometric meaning. Each extremal ray carries a geometric meaning of the original algebraic variety X. And now, a minimal model is a situation and condition where is no left-hand side half space or no extremal rays. But how can it be defined? I will not go through these details, but please consider in such a manner. So algebraic variety, when you consider 2 or 3 dimension, it's really difficult to draw anything in space, and you can see the total picture because it's of higher dimension. But we consider invariants, and we do not see invariants directly. And by drawing invariants, we try to get some objective treatment. So in a sense, it's like painting an abstract painting, a complex figure. As is the case with cone of curves, is represented by a combination of simpler forms. So in a sense, it's like a cubism. And this may sound rather misleading, so let me give you some conditions. So it could be a sort of cubism, but there has to be objectivity in this abstract painting. A painter paints an object, and in the case of an artist, a different artist would produce a different abstract painting because they are independent artists. However, in science, it has to be exactly the same thing. It has to have some objectivity and reproducibility. So art and science are very different, but in a sense that the object is not treated directly, but more or less treated indirectly. In a way, they are very similar. Paul Klee is a well-known artist, and this is one of his artworks entitled Lenient Grandpa. Circles and triangles and trapezoids are used as components. What does this pointed part mean? What does a circle mean? And that's how we audience view this painting. And this may look like a child. Paul Klee said as follows, as I went to see one exhibition of his works. He said, the role of art is not to reproduce visible objects, but to make invisibles visible. So in that sense, it's very similar to what I described of invariance. This is Paul Klee. He looked very stern and more or less awesome, very different from the paintings he painted. Now let me go back to what I was talking about. So for a curved surface, if there is just a strong positively curved surface everywhere, that's one condition. But what happens when there are weakly positively curved surfaces? First, we start with such a projective space. This is strongly positively curved surface. The second condition is P1, bundle case. Here, there are many P1s lined up in this figure. It's like a Japanese candy called Kintaro ame. Anywhere you cut, it looks the same. So P1, in one dimension, the curve is positively curved. And the third is -1 curve. There's P1, And P1 is positively curved, but other areas are not. So there are three kinds. The first two cases, in those cases, we know a certain structure of a curved surface. But in the third case, you have to contract the minus curve into a simpler one. And that contraction is possible. So if you want to study the upper figure, you want to rather study the lower figure. So that's the basis of minimal model. For a second two-dimensional case, first there is -1 curve, and that is contracted to a smooth point. And we look at this contracted figure, which is simpler. And if there is another minus curve that is contracted to a smooth point again, we continue this operation and exercise. And then it becomes either one of the three, P2, P1 bundle, and another possibility it's a minimal model. That means the absence of an extremal ray. So if you look at this by contracting a finite number of times, then it could be one of the three conditions. And each one of such a result can be further studied. What about for three-dimension case? It doesn't go exactly the same way with the two-dimension case, but there are similarities. But there is certainly a difference. There are three important differences. One is extremal ray. And second is the new operation called flip, and the third is singularities. Extremal ray. When such representations are used, you don't need an extremal curve. What you need to do is to contract the curves to a smooth point. But in the case of three dimension, by such a contracture doesn't go well. And in order to overcome this problem, you have to use an extremal ray in contracting curves into a smooth point. And a requirement of a new operation called flip, not just by contracting a minus curve to a smoother point, you have to go through another operation called flip and singularities. In the case of curved surface, after contracture, there is no problem for two dimension, but for three dimension, one of the points could become something like a black hole, and those singularities have to be addressed. So for three dimension, those are the ways to solve. And today, minimal model program is established in almost all dimensions through the contributions by many scientists, mathematicians. So we started out with a special problem, but then following our curiosity, we can lead to a very generalizable findings. And that's one of the great motivations and joy you feel. And now about rigor and beauty.
So let me describe how can we reach a solution. Of course, as I said, I am driven by curiosity, but how you come to the solution. Once your research is completed, you can evaluate how you can come to the solution. But before you complete project or research, so how you evaluate such research or project before they are complete. But thinking about that, I usually talks about the rigorous. And in an extreme sense, there's no result because project or research is not finished. Therefore, we cannot evaluate from the a rigor point of view, but beauty, whether you find the beauty or not in ongoing research, you can tell, and you can find beauty in logical consistency of a work in progress. So you can already tell when research is not complete. And so what's bring mathematician to a solution is basically the beauty. So it could be called mathematical ideas, or how can I put it? So we find beauty in a logical consistency. In my case, in the dimension 3, until the MMP was established in 3 dimension, I already had a belief in it, but my belief was based on examples and its beauty. So simply based on those examples and beauty, and I believe my project is in the right direction. And later MMP was established in all dimensions in most cases. Now let me switch gears a little bit. Let me share with you some quotes from people, especially in comparison between engineering design and mathematics. There's a person named Buckminster Fuller. He's famous because of the word flowering. And also let me introduce one of the greatest mathematicians in the 20th century, Andrew Weil. And Andrew Weil won the Kyoto Award, actually. So first, let me introduce Buckminster Fuller. He is an inventor, architect, author, and designer. And look at his head. This is called a geodome. So Florlin is famous for this geodome, and then he appeared on the cover page of Times, and he said, "Never conscious of beauty while working on a problem, but I feel that something is wrong after the work if the solution is not beautiful." So it means that you can't pursue beauty itself. Beauty can be found once you complete it. Whether beauty is there or not, you can tell after you complete it. So why I introduce this quote is because I like it. I like this phrase. But also Professor Hironaka once introduced this quote at one of the Inamori Foundation Symposium. And the next, let me introduce Andrew Weil. And he was an algebraic geometrician and number theorist. About 70 years ago, close to 70 years ago, he came to Japan, and then young Japanese mathematicians asked these questions. So first question, what is a mathematical idea? And he said, it is hard to define, but easy to recognize in a paper. So once you show the paper, I can tell. And another researcher asked this question, to whom does this occur? To whom the mathematical idea occur? And he said to people who can continue to work with other ideas. It's a little bit difficult to understand, but if you compare to the quote I introduced, a quote from Fuller, I see some commonalities between them. So curiosity and beauty, I believe, motivate me and other mathematicians in their mathematical research. Thank you very much.